Welcome to Lecture 3 in Week 1 of Differential Equations 16204. And today we're covering two important aspects of this class. The first is the existence and uniqueness of solutions to initial value problems. And the second is an introduction to mathematical models. So this second really is why do we use differential equations to model the world around us? Why are we interested in learning differential equations? And the answer is going to be basically because they're extremely useful to understand the world around us. But lingering a little bit more on point 1 here, last time, if you recall, we defined what an IVP or an initial value problem was. And if you recall, it was if we have a differential equation of certain order, if we supplement that differential equation with some initial conditions, and in fact the right number of initial conditions, then we can form something called an initial value problem. Okay, so if, for example, we had a second order differential equation, then we needed two initial conditions to form an initial value problem. Okay, and so what the first part of this class today is going to be about is if we're given an initial value problem, or if we form an initial value problem, are we guaranteed to have, or is there guaranteed to exist a solution to that initial value problem? And if so, is that solution unique? Are there other solutions, or is there only one solution? Okay, so this can be a very beneficial thing to understand about your differential equation before you start solving it, because you can spend a lot of time and energy solving a differential equation or an initial value problem. But if it turns out that initial value problem does not have a solution or does not have a unique solution, then you've probably wasted a lot of time. So it can be useful to understand when a differential equation is going to have a unique solution. Okay, so we're just going to start off by looking at the first order initial value problem. So this first order IVP consists of one first order differential equation, in this case an ODE, and one initial condition. Okay, so notice that the ODE, the first order ODE, this can be linear or non-linear. Okay, this function on the right hand side, f, is a function of x and y. I'm not giving you any conditions saying this has to be a linear differential equation. It can be linear or it can be non-linear. The initial condition says when x is equal to this number x naught, then y is equal to some number y naught. Okay, so our initial point or our initial condition is x naught, y naught. So we're going to define a rectangular region in the xy plane, which I'm going to call R. And R is basically saying x is between two numbers a and b, y is between numbers c and d. So a, b, c and d are four real numbers. And we're going to form this rectangle like so, like given here. Okay, but in that rectangle we're going to say we have to have the initial condition or the initial point, x naught, y naught. So over here, x naught, y naught is our initial condition. So now if we look at the condition f of xy, so that's the right hand side of this differential equation, and the derivative of f with respect to the variable y. So recall, if we look up at our differential equation, x is the independent variable, y is the dependent variable, and so we're taking the derivative of the right hand side of the differential equation with respect to the dependent variable. So if this function f and the derivative of f with the partial derivative of f with respect to the dependent variable, if they are continuous in this rectangular region R, then there exists some interval I naught where this interval is defined as the initial point x naught minus h, x naught plus h, where h is some positive real number, and there exists a unique function phi which is defined on this interval, which is a solution of the initial value problem. So in other words, if the function on this right hand side of the differential equation is continuous and its derivative with respect to the dependent variable, in this case y, is also continuous on some rectangular region, then we're saying that this initial value problem has a unique solution. So there exists a unique solution on some interval. Okay, so this is quite a powerful theorem. All we have to do is check where the function f of xy, which is the right hand side of the ODE, and so we have to check where that function is continuous and check where its derivative with respect to the dependent variable is continuous. And that will tell us where the initial value problem exists and is unique. Or the solution for the initial value problem exists and is unique. So an initial value problem can have multiple solutions only if the above conditions are not satisfied. So multiple solutions is not necessarily a good thing, right? We want to have a solution. So if the above conditions are satisfied, then we can be confident that we have a unique solution. Okay, so example 1, we're going to look at this first order initial value problem here. So notice that again, y is the dependent variable here. Y is not linear on this right hand side. We have a y cubed. So this is going to be a non-linear first order ODE supplemented by an initial condition to form an initial value problem. So the initial condition is x is equal to 1. When x is equal to 1, y is equal to 6. Okay, so the question is, does this initial value problem have a unique solution? Well, let's look at the right hand side of the differential equation. So recall we were calling this f. So this function f, well, this is always finite apart from when x and y go to infinity. This x squared minus x times y cubed, this is always defined and is always finite. Okay, so f is always continuous on the whole real line, in fact. Okay, so the first part of the theorem is happy, it's satisfied. But now we also need to check the derivative of f with respect to the dependent variable y. So let's take that derivative. So if we take the derivative of f with respect to y, the partial derivative with respect to y, then we're going to pull this 3 down, and well, okay, the x squared is going to disappear because that's basically a constant, and we're going to get minus 3 times xy squared. And notice also that minus 3 times xy squared is defined and is continuous on the real line, the whole real line. So therefore, because both f, the right hand side of the differential equation, and the derivative with respect to the dependent variable are continuous and finite in any rectangle that contains the initial condition, so x naught, when x equals 1, y is equal to 6, so that's our initial condition. So they're continuous on any rectangle that contains this point. The theorem tells us that the initial value problem has a unique solution on the interval x naught minus h, x naught plus h, where x naught in this case was 1. X naught is 1. And that's true for any h greater than 0, but finite. Okay, well let's look at, well, this should be example 2. So we've got another first order initial value problem, and in fact it's another non-linear first order initial value problem because y being the dependent variable is to the power of 2/3, so that's something that's non-linear. Our initial condition is when x equals 2, y equals 0. Does this initial value problem have a unique solution? Well, if we let f be 3 times y to the 2/3, or the right hand side of this equation, it's clear to see that this function 3y to the power of 2/3 is continuous and finite for any value of y. Okay, there's no problem here. This function 3y to the 2/3 is always finite and continuous for any value of y. However, if we take the derivative of f with respect to y, the partial derivative of f with respect to y, then, well, we bring 2/3 out front here, so the 3's cancel, we get left with 2. Y to the power of 2/3 minus 1 is minus 1/3. So we can write 2y to the power of negative 1/3 as 2 over y to the 1/3. So clearly there's going to be a problem here when y is equal to 0, because when y equals 0, this partial derivative is undefined, right? We're going to have a 2 over 0 situation going on. So this partial derivative, df by dy, is not continuous or defined when y is equal to 0. Okay, but this is a problem, right? Because our initial condition says when x equals 2, y is equal to 0. Okay, so our initial condition, in fact, is right at the bad point. Our initial condition is right where the derivative, df by dy, is undefined. So therefore, the assumptions of the theorem are not satisfied, and the initial value problem is not guaranteed to have a unique solution on any interval containing this particular initial condition. Okay, so the theorem doesn't tell us that anything really, except it tells us that we're not guaranteed to have a unique solution on this interval, on any interval containing this initial condition. But if I were to change this initial condition, I could avoid this problem, right? So if instead of having when x is equal to 2, y is equal to 0, if I change that initial condition and said when x equals 2, y is equal to 1, then in fact we could have we do have, by the theorem, a unique solution on any interval where y is greater than 0. Okay, because when y is 1, there is no problem with this derivative here. We get 2 over 1, which is just 2. So that's finite and it's continuous. We just have to be careful that we define the interval of our initial value problem to be somewhere that y is always positive. Okay, y cannot be 0. Okay, so the existence and uniqueness theorem is very powerful and very handy, and I believe there is at least one question on your assignment where you have to use this theorem to see if there's a unique solution to your ODE. Okay, so moving on to part 2 of the class here, we're going to move on to why we study differential equations. Okay, and so when we apply differential equations to real-world scenarios, we often call this mathematical modeling. Okay, and so here at Massey we have a third-year course called Mathematical Modeling. I think it's 16319. And so hopefully some of you will take that paper and see really the power of mathematics and how it's applied in the real world. But the point that I'm trying to make here is that differential equations are extremely useful. They're used by people in many areas of science and business and other areas. For example, engineers can use differential equations to study stresses in bridges and determine, safe limits for the operation of bridges. Business people can, or let's say investors, can use the Black-Scholes equations, differential equations, to determine the volatility of a financial market. I've already mentioned that weather forecasters can use differential equations to predict the weather and the climate and processes like hurricanes. Oceanographers can study the seas and the dynamics of the seas, and multitudes and multitudes of other applications of differential equations. So to me, differential equations are really the most practical part of mathematics. Okay. So the construction of a mathematical model basically consists of two main steps. Firstly, identification of some or all of the key variables that are responsible for changes in the system. And secondly, making a set of assumptions or hypotheses about the system. And often these hypotheses will just fall out of physical laws or common sense or people's experience, or perhaps from data that people have gathered about a system. And from this, we say we can construct a mathematical model. And so mathematical models are not necessarily using differential equations, but if any of the variables are changing over time, then they'll usually enter the model as one or multiple differential equations. So I just wanted to run through a few examples here. We're not going to solve any of these differential equations today, but this is more of a motivational, aspirational part of the course, where we're going to say, well, why are differential equations useful? And then later in the course, we're going to solve some differential equations, solve these differential equations or similar differential equations. So our first example is population dynamics. So we might like to study the rate at which a population grows. And this population could be multiple things. It could be the number of humans in a certain country. It could be in like New Zealand or Australia or Singapore or something. It could be the number of horses in the Kaimanawa Ranges. Or it could be the size of a bacterial colony growing on some cheese. And I guess depending on the type of cheese, that may be good or bad. Okay, so step one, we're going to identify our key variables. So we're going to let P of t be the population at time t. So population in terms of humans could be just simply the number of humans. Population in terms of bacterial colony could be the number of bacteria, but that's quite hard to count, I think. It could just be quite simply the area of a bacterial colony growing on some cheese. So you could just measure the area of this bacterial colony. But anyway, P of t, so I write it like this because this is telling me that P is a function of time. P is changing as time moves on. Okay, and the assumption that I'm going to make is the rate at which a population grows at a certain time is proportional to the population at that time. So rate here is a very important word. The term rate or rate of change implies a derivative with respect to time. It's saying how is the population changing at this particular time, or to write this mathematically, dp by dt. The rate at which a population is changing over time is the derivative dp by dt. Okay, and I'm saying that the rate at which this population grows at a certain time is proportional to the population at that time. So that's why I can write dp by dt is equal to k, where k is a constant of proportionality, times the population p at that time. Okay, so this differential equation is a very simple differential equation which models some simple population dynamics. Okay, and I can supplement this differential equation with an initial condition. So this initial condition says at time t equals 0, the population is p naught. So that could be 1,000,000, it could be 1,000, it could be anything, any number. Okay, so this very simple differential equation and this very simple initial value problem can be used to study some simple population dynamics. And of course there are some much more complicated and much more advanced models than this quite simple one, but this is basically the basic starting point for a population dynamics model. Okay, and in a somewhat related example, we can look at the spread of diseases. So suppose we wanted to predict the rate, the important word again, rate, at which a disease such as chickenpox spreads throughout a population. So our variables are x, and we're going to let x be the number of people that have this chickenpox or this disease. We're going to let y be the number of people that do not yet have the chickenpox or do not yet have whatever disease you're studying. And we're going to assume that the rate at which the disease spreads is proportional to the number of interactions of the two populations. So this makes sense because if all the people X are just hanging around with people that already have chickenpox, then the disease is not going to spread at all because everybody already has it. But if all the X people who have the chickenpox hang out with the Y people who don't have chickenpox, then that disease is going to spread between these two populations. Okay, it's going to move from the people who have chickenpox to the people that don't yet have chickenpox. And so we can write this as a mathematical model. The rate at which the disease, or the number of people with a disease, grows is proportional, so A being a constant of proportionality, to the interactions between these populations. And we can write this as x times y. Again, we can supplement this with an initial condition that at time t, the number of people who have the disease or have chickenpox is equal to some number x naught. Okay, and so this initial value problem is again quite a simple model of disease spread. Now there are some more complicated models of disease spread, such as the SIR model, and so the SIR model and related more advanced models are really quite useful to predict how a pandemic or a disease is going to spread throughout a population. And so governments can look to mathematical modelers to who are using these models to predict how a disease might spread throughout the country, and given the results of such a study, they can take appropriate action to reduce the harm. So it's a very, very important part of science here. Okay, and finally the last example we'll look at is a physics-based example. So if anyone's taken any high school or university physics, you'll be obviously familiar with Newton's second law of motion, and so which states that the net force on an object is equal to the mass of that object multiplied by the acceleration of the object. So our parameters, or our variables here, are F is the net force on the object, M is the mass of the object, and A is the acceleration of the object. Okay? What we know about acceleration is that it is the rate of change of the object velocity. So again, rate of change, that word, or that statement coming in there. So the time derivative of velocity is equal to acceleration. Okay, v here is the velocity, and what we know about velocity is that velocity is the time derivative of position. Okay, so velocity is the rate of change of the object position. So we have acceleration is equal to the time derivative of velocity. Velocity is equal to the time derivative of acceleration. Therefore, acceleration is going to be the second derivative of the object position. Okay, so acceleration is equal to the second time derivative of object position. So therefore, if F is equal to m times a, we can write this as a second order differential equation. So the second derivative of x with respect to t, the second derivative of position with respect to time, is equal to the force on the object divided by the object mass. And I think most people would recognize that this is an extremely common and extremely powerful and extremely useful differential equation, which is used in a variety of situations, including but not limited to studying how satellites orbit the Earth, or studying how the Moon orbits the Earth, for example. Okay, so I'm going to finish on that note there, and we will, in the next class, we will learn actually how to solve some of these simple differential equations, okay? Because to date we haven't actually solved any differential equations. We've checked if some functions are solutions of differential equations, but we haven't solved any ourselves. So we're going to start learning techniques to solve a variety of differential equations by type. So I'll see you in the next lecture.